All right, so we've been talking about the Fourier transform, and the way we started that discussion was we first introduced the complex Fourier series. And then from the complex Fourier series, we were able to rewrite this complex Fourier series. We were able to rewrite it to make it look like a Riemann sum. And then we converted this complex Fourier series into an integral. So one point I would like to make about this complex Fourier series, I mentioned this minus infinity to infinity type form. It's very important that we interpret what that means. And so I've added this extra statement here to this fun fact slide, that the series that we're looking at that goes from minus infinity to infinity should be interpreted in this form. That is, when we look at this series from minus infinity to infinity, we're thinking of its partial sums as being this form, from minus capital N to capital N. So this would be what a partial sum would look like. And then we take this N right here and send it to infinity. And that gives us this minus infinity to infinity type term. And Jacob had asked a question, basically, clarifying that when we cut off the series, we have to do so in this symmetric fashion. And so this comes back to that point. And, and I think the reason is that if you look at our basis elements, we always take our basis elements in basis pairs. We always look at the cosine and the sine, because you need both of those. Even if you cut it off, we always take full complete pairs of basis elements, cosine and sine. So here, I think it's the same issue here, that we need complete basis elements. The way we arrive at this series is we rewrite cosine as a linear combination of e to the I and e to the minus I, and similarly, we rewrite sine as a linear combination of e to the I and e to the minus I, and then break that up. But at the end of the day, we need to have this kind of balanced basis where you have e to the I and e to the minus I. So, Evan.
So in a complex analysis, when we take contour integrals, we often take the Cauchy principal value, where we let the upper and lower limits diverge like simultaneously. So this is like a discrete version of that, right?
Exactly. And actually the transform is exactly a Cauchy principal value. So yeah, this is a discrete version of that. And now when we go to the transform, let me show you, that's a exactly what you said, a Cauchy principal value. So, and I wanted to clarify that. Yeah, great comment. Yeah, no, thank you, Jacob. So here, I wanted to exactly what Evan was mentioning. So here we've defined the Fourier transform now. The Fourier transform is just the Fourier coefficient of f of x, right? Here, f hat of m, that's just calculating the coefficient using the projection formula. And here's our data. Here's our data. And then we project it against, the basis element, and then we're normalizing it, So that's the Fourier transform, is just the coefficient. Now the inverse transform, and this we developed, using by rewriting the complex series as a Riemann sum and doing a limiting procedure. This inverse transform, and what this is actually the Fourier series. So you call it the inverse transform. It's really, this is our Fourier series. So here, when I look at this, the way I try to see this is, so here's our sum, here's our Fourier coefficient, here's our basis element, and here's dm. With the series, the dm part is usually just 1 in the discrete case. So this inverse Fourier transform is actually a Fourier series, written in this Fourier complex series here, written in this integral form. So this now, as Evan said, should be interpreted as what we call this Cauchy principal value, in that the integral, this infinite integral, should be viewed as the limit of the integral over this symmetric region minus n to n, and then we send n to infinity. You know, so there's a little bit of calc 2 that I should go into, because, you know, what's the issue here? Let me just kind of back up a little bit and do some calc 2. Okay, so let me clear off some space here. And so in calc 2, what we learned is if you have an integral from minus infinity to infinity of f of x dx, then in regular calculus, the way we interpret this integral is we first break this integral up. So I would break this integral up minus infinity to a f of x dx plus integral from a to infinity f of x dx. We first break this up, and then we treat each individually as a limit. So now here I would do a limit here for this first integral, where the lower bound, so I call this t, I guess. So I call this a, squeeze in the f here. And so here we send t to negative infinity. And then we do another limit here for this divergent upper bound. I guess I'll just call this s, and send s to plus infinity of f. So in calc 2, this is how we were taught to interpret this integral. This Cauchy principal value is a different creature. So here what we're doing is we're saying interpret this now as this integral from minus capital N to N of f. And now let's take a limit and send capital N to infinity. So that's the thing. It's kind of this subtle analysis point, maybe a complex analysis point, that we're not actually interpreting. And here I should be careful. I should make this a DM. I should, you know, that doesn't help when I write this as a, I should really be a little more careful. But anyway, that's what's happening here. We're doing this other type of interpretation. And so that's what this is. And I'll come back to this one more time, okay? And so that's the thing for this particular, you know, we call it the inverse transform, but it's really the Fourier series. It's our Fourier complex series written in integral form. That's what you should see there. Don't let the language mess with you. That's our Fourier series with its coefficient basis, you know. And here the Fourier transform, this is just the coefficient of the function. And, you know, we treat the function and the coefficient basically as being the same thing, because you can find one from the other and vice versa. So, yeah, we had seen these fun facts. And one thing was that this, if our data is what we call absolutely integrable. So now this integral we're interpreting in the usual way. So that's the thing. This integral, where it's an integral with respect to dx, we're going to interpret in the usual way. Okay, so here I'm not thinking of this with the minus infinity. I'm not thinking of this as a Cauchy principal value. It's this other integral here that's in M, this dm integral. This is the integral we're thinking of as the Cauchy principal value. This integral up here, which is in dx, this is just a good old Riemann integral that we know from Calc 1 or 2, you know. So if our data is absolutely integrable, then we can show that the Fourier transform is also going to be bounded. The Fourier transform will be directly bounded. One comment to make here is this e to the imx or e to the minus imx, that's, you know, you should be careful with your intuition. That's not a traditional exponential function. Once we bring in the complex, remember, this is actually an oscillating bounded function. E to the imx is just a very fancy way of writing cosine mx minus I sine mx. So that's one thing you should really be careful when dealing with this complex form of the exponential function. It's totally a different animal than the real version. Here, this is a bounded function. Okay, so you can take the complex norm, the modulus, and show that the modulus of e to the I mx or e to the minus I mx is 1. So here we can show that if f is bounded, then so is f hat the Fourier transform. We saw this before, the 0th coefficient, really f hat of m, we should think of this as the Fourier coefficient. And the 0th coefficient, with a regular Fourier series, the 0th coefficient is typically the average of the function. And so here we're getting some type. It's not necessarily the average because here you're dividing by 1/2 pi. But if you imagine the domain is kind of circular, then you can kind of think of this as some type of averaging. But anyway, it's the area of the curve divided by 2 pi, the 0th coefficient. So here is this new result that I added on convergence, and I've re-uploaded these slides with these new results. And so here, this is the convergence result for when the so-called inverse transform converges. Remember, the inverse transform is really just a Fourier series. So here we have f of x has to be piecewise smooth, and it's absolutely integrable. Then for each x, here's our convergence result of the so-called inverse Fourier transform. It's really just a Fourier series. Okay, so here's the coefficient times the basis element, and we're summing everything. Okay, this is where we interpret this as a Cauchy principal value. So when I write the equal with the CPV above it, it's just to remind us, okay, we're interpreting this now as a so-called Cauchy principal value. And so now we're simultaneously sending the upper and lower bound, we're allowing them to simultaneously diverge. And so the convergence theory says this will converge to, the average from the left and the right at the point x. If it's continuous, it'll just converge to the point. So yeah, here's that Cauchy principal value interpretation of what is essentially, this is a Fourier series. I mean, I think that's, for me, that's really the thing to keep coming back to, that this is a Fourier series, really. It's just written in this weird integral form, but there's your coefficient, your basis, your sum. Yeah, in general, if we just interpret this integral in the usual way, then it in general will not be absolutely convergent. So this integral interpreted in the usual way may not be well defined. And so here it's important that we interpret this as the Cauchy principal value. And again, this convergence result, I think, is exactly why when we cut things off, we have to cut them off in a symmetric manner, in regards to Jacob's question. Evan.
So that integral from -infinity to infinity of the absolute value of f of x, is that a Cauchy principal value, or is that
I don't think so. I think this is just a regular integral. I don't believe this is. Yeah, just this thing with the dm. And that's kind of what I use to kind of make sure I'm oriented. What are we trying to integrate out here? For this integral, we want a function of x. We want to end up with a function of x, so we integrate out the dm. This is our Fourier series, But yeah, this is just a regular type of integral, Evan, versus the other one. Versus this is the Cauchy principal value with the dm. Yeah, it's a good question. So here's just an example, a mechanical example of doing a Fourier transform. Basically, I want to find f hat of m if f of x is this function here. And you can see how it's defined. It jumps up between minus L and L. Outside of minus L and L, it's 0. And I've averaged it at the discontinuity, just to make it Fourier friendly. So here, just a mechanical problem. We just want to find f hat of m. So So I just want to do the formula. So now here's the part where you should think it through. I want to find something that's a function of m, so I'm going to want to integrate out the x variable. And so here, the formula we've developed is 1 over 2 pi integral negative infinity to infinity f of x e to the minus mx dx. We're integrating out the x variable. The m will be the working variable on both sides. And you know, depending on which book you read, you might have a slightly different notation. So I think Haberman has an e to the imx here and the minus on the other transform. And some books will have a 1 over square root of 2 pi in front of both transforms instead of having a 1 over 2 pi. So depending on which book you read, they will tend to have slightly different, you know, protocols. So here I'm just doing the integral. The integral's from minus infinity to infinity, but the function, you know, the complex support is only inside minus L to L. Outside minus L to L, the function is 0. So the integral from minus infinity to minus L, that's 0. The integral from L to infinity, that's 0. I just have this one integral where x is between minus L to L. And in that domain, the function is a. So I replace f of x here with a when x is between minus L and L. And a is just a constant. So here I'm just integrating e to the minus mx in the usual way. So here the antiderivative of e to the u is e to the u. Antiderivative of e to the ux is e to the ux over u. So here I have this divided by minus im. And we can always check by taking a derivative. If I take the derivative, you get a minus im, which cancels. And so then I'm doing the old f of b minus f of a, evaluating it. And so I get this answer here as my Fourier transform, the coefficient. And technically we're done, but here I just want to clean this up a little bit and introduce a well-known function known as the sinc function. So here, we're going to bring the 2i, so there's this 2i right here. We're going to bring that 2i inside and write this as e to the iml minus e to the minus iml over 2i. So this 2 and this I got brought inside here. And now we can interpret this e to the iml minus e to the minus iml over 2i. That should look slightly familiar to you. That's the sine function. That's just, you know, you can use Euler's formula to show that equals the regular sine of ml. So one final step here. I'm going to bring this m down here underneath. So bring the m right here, divide by an L on the bottom and multiply by an L on the top, and write this as sine of blah divided by the same blah. So sine of ml over ml. And so here, the m got moved, and I'm multiplying top and bottom by a capital L. So yeah, in complex variables, this function here, the sine of something over that same thing, sine of theta over theta, that's called the sinc function. So sine as in sine, and then c as in complex. So you'll see this function comes up in complex variables. The c part is for the word complex. So yeah, the sinc function is defined to be this sine of blah over blah. And so here I can write the Fourier transform of f of x as al over pi times the sinc of ml. And, you know, remember, this is actually, the Fourier transform is actually the coefficient, the Fourier coefficient. So we can use the Fourier coefficient and stick it into the Fourier series. And if the function is well behaved, we know our Fourier series will converge to f of x. So just to kind of orient you, you know, it's kind of easy to get disoriented now. The Fourier transform is really just a Fourier coefficient. You know, if you look at the formula, you can see it's using f of x, basis element, and this right here is our projection formula. It's just that m now is real. With our Fourier series, you know, our index is discrete. Now our index here is a spectrum. That's very different. So as I mentioned, if you, depending what book you read, you'll see they use different types of notation. So you should be careful. The notation I've used is different from what Haberman has used. And so if you replace n with negative p, then you'll get Haberman's notation for both the complex Fourier series and the transform. And Haberman uses this notation. Pinsky's book or Power's book or other books use this notation. This is the notation I'm using. I figure rather than do the same thing as Haberman, I'm going to force you to learn it both ways, because that at the end of the day is the best thing for you. What you should really key in on when you look at both these formulas, you should see that f of x in both cases is kind of acting as the input. In both cases, they're taking f of x and then doing some type of projection formula. In one case, we're using e to the minus I as the basis element. E to the minus I as the basis element. And in the other case, we're using just e to the I. You know, I mean, it's just kind of a stylistic choice because you have these two orthogonal basis elements, and now depending on how you've indexed things, you know, you could get one or the other, but we should understand it not just mechanically and formulaically, we should understand what's going on. And in both cases, what you should key in on is, oh, it's taking f of x and it's using f of x to figure out what it is. And so here, this is the coefficient. In both cases, this is the coefficient. And here for the, you know, the so-called inverse transform here, the Fourier integral. So Haberman writes it in this form. And in my notes, or in Pinsky's book or Power's book, we're using it this form. Again, what's the big difference? The big difference is the basis element being used. However, in both cases, you know, the end result is you're getting the f of x function out. And so you think, how do you get f of x? Well, you have to make the Fourier series. You have to take the Fourier coefficient, multiply it to the basis elements, and add them all up. And that's what we see here. And so then we can realize, oh, this expression here is just a Fourier coefficient. This is just a Fourier coefficient, or what we call the transform. So yeah, just be careful if you read Haberman's book, is all I'm saying. And like on a homework, I'll define the Fourier transform so that on the homework, there'll be everyone use a particular definition of the Fourier transform. So on the homework, right at the beginning, I'll define how I'm defining my transform, and then that'll be the consistent version that we use in the homework. And of course, this won't be on a test because there's no final. And yeah, you know, a lot of this is working. You can do a simple integral change to get from one to the other. It's just like I said, just a simple change of variables to get from one to the other. And this is speaking to that change of variables, where if you change from x to minus x, you can flip-flop between one form to the other. So that ends the discussion of the Fourier transform. I now want to switch over and use the Fourier transform to solve a heat equation, because now I want to come back to PDEs. So let me switch over to the other slides here. All right, so now I've switched over to solving the heat equation on the entire real line. So this is slightly different. So the first slide was just meant to remind us of the complex Fourier series, the Fourier transform, which really, the Fourier transform really is just the Fourier coefficient of f of x, and the inverse transform. The inverse transform really is using the Fourier series and the coefficient to recover the function f of x. And this inverse transform we interpret as a Cauchy principal value. So we're now back to the heat equation, everybody. The only difference now is we're not looking at a rod of finite lengths. So as you remember, before we had our heat equation, we had this rod of length L. We had x going from 0 to L. And you know, we talked about what was going on there with boundary conditions and blah, blah, blah. So here, there's no quote unquote ends of the rod. This is an infinitely long metal rod here. We have an initial temperature, and we're given that this initial temperature is absolutely integrable. You know, it's understandable now that we're dealing with a domain that goes from minus infinity to infinity. We're going to have to specify, you know, these little details, these little technical details about this improper integral. It needs to exist for this to even first make sense, right? So these are math technical issues. Okay, so I need this integral to be to make sense on minus infinity to infinity. And here we don't have a traditional boundary condition. Usually we talk about, are the ends insulated? Are the ends connected to some kind of bath? You know, we have these different scenarios, but here, the only boundary condition we give is we say that the temperature should be bounded for all space and time. We don't want the temperature to go to infinity or negative infinity. That's the only, you know, so that's why I put boundary conditions in quotes here. So, and again, you know, this boundary condition, mathematically, we wouldn't necessarily have to have that restriction, but it is sort of coming from the physical analysis of what's happening here, you know, that this is temperature. So some books, I'm not sure if Haberman does it, I can't remember. Some books will use this as the boundary condition. They'll require this limit and they'll have that in place of this statement here. So it's not, that requirement is actually too strict, and it can make the separation of variables kind of break down in certain places. So I think Haberman might have done it. I'll have to double check. And, you know, I'll try and come back to this point, but yeah, we don't use this particular type of boundary condition. It's not conducive to separation of variables. Instead, we choose to use this boundary condition I've specified up here. So we claim the set of functions that satisfy the PDE and boundary conditions forms a vector space. Remember that whole thing? And so now we claim we can use separation of variables. And so now all of this should start flooding back like, you know, good old friend. We let u of xt equal f times g, and we assume it's not equal to 0. And then we use the heat equation to separate the variables. Careful, here I'm setting this equal to lambda, okay? When we did separation of variables on the finite rod, we set it equal to minus lambda because we ended up, it looked nice in the solution. Then when you wrote the formal series solution, you got this nice term, which you could see was exponentially decaying. You could look at it and you saw it had all positive exponents, and then there's a minus sign in front of it. So it looked really nice. And you could just visually look at it and go, aha, there's this exponentially decaying term. Here, we're not going to write this as a formal series solution. We're going to write this as an integral. And so we don't need any of those types of cosmetic details, aren't necessary here. You know, there for the formal series solution, it looked nice. We could look at it and go, aha, there's a decaying exponential term. Here, we don't need that. Okay, so be careful. This one detail is different from how we do regular separation of variables. And certainly you could use a minus lambda there if you wanted. You know, it's, again, to some extent, it's a matter of choice here. But I don't want you to get confused and say, hey, wait, this looks different. This is slightly different. So here we get this X domain problem. Again, for emphasis, this is not a minus lambda, typically it is. And then we get our T domain problem. And now we do the usual thing. We look at the cases, the different cases for lambda here. What if lambda is greater than 0? What if lambda equals 0? What if lambda is less than 0? For lambda greater than 0, we get exponential functions. You know, you'd get r squared equals lambda, where lambda is positive. You know, when you plug in your characteristic equation would look, so in the lambda greater than 0 case, your characteristic equation would look like r squared equals lambda, but lambda is positive, so I can take a square root. I get r is plus or minus square root lambda. And so now when you plug it into the e to the rx, I have a pair of unbounded functions. We get exponential, because these aren't complex. That would be e to the rx. That would be e to the square root lambda x. It's not complex because lambda is positive. So these are good old-fashioned real exponential functions. When you send x to infinity, one of them will blow up. You send x to negative infinity, the other one will blow up. So in the lambda grids, you know, we can't have any exponential solutions because they're not bounded. If lambda equals 0, just go back to the original ODE, replace this side right here, get rid of all this, replace this with 0, and integrate twice. Integrate twice, I get f of x equals ax plus b. But now if you send x to plus infinity or x to minus infinity, this term is going to blow up. The ax term is not bounded, so a must be 0. So for lambda equal to 0, we do get, there's this constant eigenvalue. Lambda equal to 0 is an eigenvalue, but you know, it's a constant. And now I want to consider the lambda less than 0 case. Okay, so here, let me write lambda as negative m squared so that we can clearly see that it's negative for any real number m. So as always, you let f equal e to the rx. We get our characteristic equation, r squared equals lambda, replace the lambda with minus m squared, and then take a square root, we get r is plus or minus im. So you should notice, okay, this is complex. So we have this basis for our solutions here. And so, you know, by superposition, this linear combination forms our eigenfunctions. And here, we don't eliminate any of these. This is the part where I really want you to, you know, be careful. You know, if our intuition tends to like to always treat the exponential function e to the whatever as blowing up. Here, e to the imx and e to the minus mx are not your traditional type of exponential functions. They are bounded oscillating functions. E to the imx, you should really think of that as cosine. E to the imx, you should really think of that as cosine mx plus I sine mx. And e to the minus imx, you should think of that as cosine mx minus I sine mx. Okay, these are bounded oscillating functions, and so there's no issue here. They satisfy the boundary condition. They satisfy the ODE using, you know, superposition. For the ODE solution, we can form this linear combination as a solution of the X domain problem. So that's the one thing I would just keep coming back to remind you that e to the imx, e to the minus mx are bounded oscillating functions. So now we go to the T equation, and here I replace lambda with minus m squared here. This is the case lambda is negative. And then we can solve this in the usual way, which is just to remind you, we use ODE's separation of variables, bring the g of t over, integrate both sides, you get ln of g, and then e both sides. So we get g equals some constant e to the minus m squared kt, just as usual. And, the constant here, we would use the initial condition to find. So now we have our solution to the x domain problem, solution to the t domain problem. So we can put these together to create our product solution for each m. And here, let me just emphasize, we have now a spectrum of eigenvalues. In general, anytime you see the word spectral, spectrum, there's probably eigenvalues lurking in the background. The word spectral or spectrum, typically is in reference to an eigenvalue problem, and spectrum as opposed to being discrete. So now by superposition principle, we can sum all of these product solutions, but remember here, we're summing over all real numbers. So here we're summing from minus infinity to infinity with an integral. And so that's what you see here. I'm summing, and here I'm taking the product solution, where you have, I've distributed the t solution across the solution to the x domain problem. And what you should see here, we've got an x variable, and then we've got our t variable. And you should really just think of this integral as a Fourier series. Here's the coefficient of the Fourier series. Here's the basis element for x and t. And then here's the sum that we're summing this whole thing. So really, I think it helps to see this as a Fourier series. Now, in this case, because we're integrating from minus infinity to infinity, this second integral is actually redundant. If you look at this second integral, since we're going minus infinity to infinity, we can just use a change of variables and make it look like the first integral. So here, if we replace the m with a negative p, the integral flips around, your bounds change sign, but because the integral flips around, everything ends up looking the same. You get a minus sign here. These get negated. Here, this negative im has now become just an ip because we replaced the negative m with a p. Right, so here, this is in play. And now if we apply the minus sign and flip the integral, it looks exactly like this integral here. The only difference is the dummy variable. One's in p, one's in m. So at the end of the day, we write our series solution like this. Here now is our, well, I guess it's not a series anymore. Here's our formal integral transform solution, because it's not quite a transform because it's got that kt term in it. When you let t equal to 0, then it'll look like a proper transform. But yeah, I hope you can kind of just see the analog of a Fourier series solution. Here's our sum. Here are our coefficients. Here is the basis for the x variable problem. Heat equation would be sine plus cosine, which is basically what that is. And then here is the basis for a t variable problem. In the heat equation, it was a decaying exponential function. That's what I have. And the whole thing you should think of as this Cauchy principal value, think of it as a Fourier series. In the discrete version, the dm is just a 1. In the discrete version with the actual series, the dm is just a 1. But yeah, when you look at that, don't let the notation mess with you. Keep coming back to saying this is a very standard looking Fourier series, except it's written in this continuous form. So now we can use the initial conditions to find the coefficient a sub n. The initial condition, when we let t equal to 0, this part's going to disappear. When this part disappears, the part with the t variable, then what you have is, you know, an inverse transform. So now let t equal to 0. The time decaying term disappears. And what we're left with now, so time decaying term, what we're left with now, if you look here, this is now exactly, you know, what we call in the form of an inverse transform. And you can take the transform of both sides and invert it, or you can use the fact that we know u hat equals, we can write u of x in this fashion using the transform. So you should see a Fourier series here. Here's the coefficient. And so by comparison here, a sub m is equal to u hat of m. A sub m is the Fourier transform of the initial condition. And so here it is in one box, everything together. Our solution to the heat equation on the entire real line is this integral, which is a Cauchy principal value. And we can use this formula here to find the coefficients. So this u hat of m, that's what we're calling, that would be what we call the Fourier transform of the initial condition u of x. And here, this is a, you know, basically a variation of the inverse transform. So yeah, the solution at the end of the day, you know, and of course we don't do that separation of variables every time we solve the heat equation. Now that we've done it once, we now know this is the solution to the heat equation for the rod on the entire real line. And you say, is that practical? Well, it's actually not as impractical as you might think. If we now combine this with the method of images, we can use this to solve even the finite heat equation for a finite rod. Take the initial condition for the finite rod, you know, and this would be where we have Dirichlet boundary conditions, okay? Take the initial condition, do a odd extension, because the solution of the original heat equation is a Fourier sine series, so just so that that theory matches up. Do an odd extension of the initial condition, and then do a periodic extension of that to minus infinity to infinity. Method of images. And then solve that problem using this technique. And then by periodicity on minus L to L, I mean, the solutions should coincide. So we'll actually talk about all that in this set of slides. I won't get to it today, but on Wednesday, we will go through it and do that, exactly that. Okay, so I'll show you the method of images, and we'll solve the finite rod solution using this technique. So here we can show the Fourier coefficient is bounded. We can show the 0th coefficient is kind of this similar average term. It's not the average exactly, it's the area divided by 2 pi. If you kind of think of the domain as being circular, then you can sort of heuristically think of that as kind of an average. And here, I just went through the equations here. The only thing I want to remind you here is that this is a bounded function. The modulus here is equal to 1. Okay, so that's the only part where sometimes it's confusing when people see, we go, hey, isn't that exponential? How'd you make that go away? Well, the modulus here is 1. That's why it just disappears here. Because e to the minus imx is actually cosine minus I sine mx. And if you take the norm of cosine minus I sine mx, you multiply it by its own conjugate, you get cosine squared plus sine squared. You get cosine squared minus I squared sine squared, but minus I squared is just plus. You get cosine squared plus sine squared, you just get 1. Okay, so that's the only part that I think is a little bit tricky, that can mess with people. This bounding result here is actually one of the results of the Riemann-Lebesgue lemma. And so this is kind of the more general Riemann-Lebesgue lemma for Fourier integrals, or for inverse transforms, however you want to think about it. And let me just show you this statement, and then I'll stop here. So I've done a light proof of each of these on the next couple of slides. And then, you know, I talk about using method of images to solve the finite rod problem on the next couple of slides here. So here, suppose our initial condition u of x is defined for x between minus infinity to infinity. And here, you know, we define the Fourier transform of this function in the usual way. If you're looking at Haberman's book, he wouldn't have that minus sign there, you know. And so now, if our initial condition is absolutely integrable, then the Riemann-Lebesgue lemma claims that the Fourier transform of the initial condition is bounded. We've proved that. It's continuous in M as a function, and u hat of M goes to 0 as M goes to plus or minus infinity. So Riemann-Lebesgue lemma, you know, very famously was about oscillatory cancellation. And this is the oscillatory cancellation right here. Here, um is this integral. And here, as M goes to infinity, you should think of this as a wave. You should think of e to the minus imx as a wave. And here, this is as x, you know, as here, when we say this goes to 0, we're saying when you integrate, the area above and below the x-axis are canceling out. And so this third statement is exactly the statement regarding oscillatory cancellation. Remember, u hat of M is really this integral that's disguised. And what's this integral? It's a function times some oscillating term. And so saying that that goes to 0 as M goes to infinity, here's M goes to infinity. M's the frequency number. M here directly has to do with the period. Remember, e to the I minus I mx is cosine mx minus I sine mx. So as we send M to infinity, the frequency starts to become greater and greater, and you have more and more overlap of the region above and below the x-axis, and they cancel out, and the integral goes to 0. Okay, so this is where we're having that oscillatory cancellation that we talked about, that we used way at the beginning of the semester when we were trying to do our convergence proofs, because this is exactly the coefficient of the Fourier series. You know, in the series, it wasn't the cosine and sine that would have messed up the convergence, it was what the coefficients were doing. So yeah, so, you know, essentially, as long as our initial data is well behaved, the Fourier transform will be okay, will also make sense. And here, you know, we have this oscillatory integral cancellation, which kind of makes things work, at least when we're looking at it from a series point of view. So, you know, the oscillatory cancellation also implies we can truncate u hat of M without too much data loss, you know, for large M. So I'm going to stop here. This is my time. So what's to follow on the next couple of slides is a light proof of the Riemann-Lebesgue lemma. And then I'm going to use method of images to solve the finite rod problem using the infinite rod problem. And we'll also derive what's called the fundamental solution, which will lead us to a bell curve. Okay, so there are connections here to probability theory as well. All right, so I'm going to stop right here. I want to thank everybody for your time.